This video is all about Chapter 16, Carbohydrates, for Chem 111. Let's go over some basic carbohydrate facts. They are produced in plants by photosynthesis. When they are burned, 1 gram of carbohydrates equals 4 kcal, or food calories, of energy. Complex carbs make a great energy source. They often talk about eating pasta and things like that the day before a big race. And it is said that 45 to 65% of your calorie intake should be carbohydrates. There's a variety of different types, which we're going to cover in more detail in the next couple of slides, eventually throughout this PowerPoint. Monosaccharides are single sugar units, for example, glucose or fructose. Okay. Single sugar units often have the chemical formula, and again, it depends on their total number of carbons, of C6H12O6. Okay. Both glucose and fructose have the same chemical formula. They are isomers of each other because they do not obviously look exactly the same. Disaccharides are when you have 2 sugar units joined together through a bond. We will talk about those bonds a little later on. And some examples there are sucrose and lactose. And the chemical formula for these is C12H22O11. Okay, so almost double what we have for a monosaccharide, but you will kind of notice, hopefully, that it would be 2 less H's and 1 less O than exactly double. And that's because, of course, H2O is water, and that is what is lost to form these disaccharides. And finally, we have a variety of polysaccharides that we're going to talk about in great detail. They are long, they are highly branched chains of monosaccharides, and these include things like starch, glycogen, and cellulose. Let's dive a little deeper into monosaccharides. Monosaccharides are composed of C's, H's, and O's, of course. Okay. They are often classified based on their functional groups or the number of carbons they have within their main skeleton. Okay, so if they're classified by their functional group, they actually usually combine them, and you'll see that down below. A ketose, of course, contains a ketone functional group. So you have an O double bond C to other C's. And an aldose, of course, contains an aldehyde functional group. So somewhere in the structure is an O double bond C to an H. They can also be identified based on their number of carbons. Okay, you'll notice that pretty much all of these end in O-S-E, very similar to how alkanes were all A-N-E, and alkenes were E-N-E, so on and so forth. So a triose has the prefix tri, which means 3. So a triose is composed of 3 carbons. A tetrose, obviously tetra, is composed of 4. More often than separating them, you actually will see the classification system combined. So you can see some examples right here. We have an aldotetrose or a ketohexose. Okay, and what I'd like you to kind of notice is there's example pictures of each of these. This one right here has 4 total carbons. 1, 2, 3, 4. So it's a tetrose. And I'd like you to take note that this up here is an aldehyde. So there's your aldotetrose. Okay. And then over here, this is called a Fischer projection. We're going to talk about those in a lot more detail shortly. Okay, you're going to learn how to draw them and things. But very similar to our organic chains, right, where the bends and the ends are carbons. Now the intersections are carbons. Okay, so there's a carbon here, there's one here, there's one right there at that intersection, here, here, as well as here. So there are 6 carbons in this structure, And I would like you to take note that there is a double bond OC in the middle of the chain, not on the end. So it is a ketone. So this is a picture of a ketohexose. Okay, so this picture right here represents that. Okay. Some things you are going to need to be able to do is potentially, once we learn more about the Fischer projections, look at a Fischer projection and determine the type of carbohydrate that I have. Is it an aldose or a ketose? And, what other numbers go with it? Does it have 5 carbons? Does it have 7? So on and so forth. Okay. In addition to determining if something is an aldehyde or a ketone and telling me the number of carbons, we have 2 types of stereoisomers that exist. Okay. A stereoisomer we'll cover in more detail on the next slide. Okay. But it's all about the spatial arrangement of the atoms and where certain things are found. So for your stereoisomers, you can have a D sugar or an L sugar. D is if it is a right-based sugar, and L is if it is a left-based sugar. Okay, and then you can see here in the picture, they base the D and the L off of the oxygen that ends up reacting with the aldehyde or the ketone. Okay, it is always the oxygen that is on the last chiral carbon, okay, which we'll talk about as well. That means there's 4 different groups around the center. So you're going, and basically it's the oxygen that's furthest away from the aldehyde or ketone that is on a chiral carbon. So for this example here, D-glucose and L-glucose is based on this OH group. Notice that this OH group is on the right side of the molecule, where this OH group is found on the left side of the molecule. Okay, so that's how we determine D and L. It's always based on the last OH, the furthest one away, that is on what we will call a chiral carbon. Okay, all right, so let's kind of dive into this a little bit deeper on the next slide. So stereoisomers are a pair of molecules having the same structural formula and bonding pattern, but differing in their atomic spatial arrangements. Okay, so I'll put another example here. All right, again, you're looking at the OH group that is, the furthest away from the aldehyde or the ketone that is on a chiral carbon. Okay, and again, chiral carbons have 4 different things around the center. We have briefly talked about them before. So for this example here, we have the OH here, right? And we have the OH here. Okay, it's basically the OH that's on the second carbon from the bottom always. So we have our D-glyceraldehyde and our L-glyceraldehyde. Okay, remember again, D means right and L means left. So this one would be D because it's on the right, and this one would be L because it's on the left. Okay. Let's review a little bit about stereochemistry. Stereochemistry is the study of a spatial arrangement of atoms within a molecule, okay, related to stereoisomers. Okay, and we don't really get into a lot of detail with this in here. This relates to organic chemistry as well. They have the same bonding pattern, but the molecules are not 100% identical. They behave differently when it comes to like polarization and magnetic and electric fields and things along those lines. Okay, so I want you to kind of just take note of the slight differences in these molecules. They really are pretty much mirror images of each other. Okay, and so you can see here in this example, the Br is on the right side. Okay, and over here, the Br is on the left, so the molecule has rotated. These are often referred to as an enantiomers, I think that's how you say that word, of one another. Okay, mirror images of one another. So they're slightly different, just like the D and the L are slightly different because the molecules are rotated differently, which means they may have some different behavioral properties. Okay. Moving on. Let's continue our study on stereochemistry. Okay. I've said the word chiral quite a few times here. Chiral molecules are molecules that exist in the enantiomer form. Okay. Things that are chiral have to have at least one chiral carbon. Okay. And a chiral carbon is 4 different groups or things around the center, very similar to things that are polar. Okay. The simplest one that does exist is our glyceraldehyde, excuse me. Okay. So if you look at the carbons that are present in this molecule, okay, we have a carbon here, here, and here. Okay. We're looking for the carbon that has 4 different things around the center. So if we look at this first carbon, we only see 1, 2, and then this whole group below would be 3. If we look at the carbon on the bottom, it's indicating to us that there are 2 H's on it, as well as an OH, and then also this whole group here. So it also is not chiral. The carbon in the middle, however, is a chiral carbon because it has 1, 2, 3, 4 different groups around the center. So this is your chiral carbon. Okay, it's different groups, not bonded to different things, right? It's carbons, they're just different carbon groups. Okay? So these chiral molecules, and depending upon how they're formed, have different optical properties. They rotate polarized light in different directions. Okay? They can rotate the light clockwise, or they can rotate the light counterclockwise. Clockwise is said to be positive. Okay? And this relates to our D sugars. Counterclockwise is said to be negative, and this relates to our L sugars. We have something called optical activity, okay, which is directly related to these optical properties. We have mixtures of them. Racemic, probably not how you say that word. But this is a combination of the positive and the negative sugars. Okay, and they kind of cancel each other out. Something goes clockwise, something goes counterclockwise, cancels out. So these are said to be optically inactive when there is a mixture of the two and they're fairly equal. Okay, they are inactive because we have an equal amount of positive and negative. Okay, we also have some where they can be separated, and then their optical activity is called achiral. And depending upon which one we're looking at, right, if it's a D sugar or an L sugar, it's going to be optically active one way or the other. So these are optically active because it's just one type. Okay, and they are either positive or negative depending upon what we are dealing with and what we have present. Okay, on the next slide, we're going to talk about how to draw these stereoisomers appropriately. These drawings are called Fischer Projections, developed by Fischer, obviously, hence the name. They are 2D models or 2D drawings, so flat drawings of a molecule with a chiral carbon. Okay, the chiral carbon is at the intersection of the two lines. Okay, so they don't usually show the carbon, similar to some of the images we've already seen. Okay, we know that molecules are not flat, right? They are 3D. So in these Fischer projections, our vertical lines are said to be substances that are projecting into the page. Okay, and in the past, we've briefly mentioned that this is a dashed line like that. And our horizontal lines are projecting out of the page. And again, in the past, we've done this as a solid line. Okay, so for example, and then we'll do that example at the bottom there. Okay, we have something like this. So here's our molecule, and you can see some of them are projecting out of the page, some of them are projecting into the page. So if I turn this into a Fischer projection, it would look like this. I don't draw the C is at the intersection, okay? And then I would have H and F here, all right, because they're vertical, they're going into my page. And I would have Cl and Br here, because they're coming out of my page. Okay. So that's a very simple example. We're going to do another slightly more difficult example below. And then you guys will get a chance to try one. So the number of possible stereoisomers is usually based around the number of chiral carbons. Okay. And I try to keep this pretty simple on testing and on homeworks and stuff for you. Okay, so this N right here is your number of chiral carbons. Okay, so I'm going to do the example. It says, write out the stereoisomers for a 2,3-dichlorobutanol. Okay, butanol, of course, is an aldehyde. Okay, so I'm going to just kind of draw it like I normally would first, and then we'll convert it. So but means 4. So it's going to be a line structure here, 1, 2, 3, 4. It's got the OH. Okay, and then there's a chlorine here, and there's a Cl here. Sorry, the calibration appears to be slightly off on that portion of the board. Okay. And of course, we don't normally show these, but I'm going to add in my H's. Okay, so there's an H here, there's an H here, and there's of course 3 H's on that carbon there. Okay, so we're going to go ahead and we are going to draw out our Fischer projection for this based around our chiral carbons. Okay, when we draw a Fischer projection, we only do not connect the H directly to the carbon if it is chiral. Okay, and you'll see what I mean in a minute. So if I turn this into the first possible Fischer projection, okay, I know there's a total of 4 carbons. I have 3 major points of intersection, right? So I have this carbon here, which is not chiral, this carbon here, which is, this carbon here, which also is, and then this final carbon on the end, which is not. Okay. The only ones that you show like this, like an intersection, are the ones that are chiral. So in this example, we should have 2 crosses basically put together. So I'm going to draw that. Okay. I have 2 chiral carbons, so I should have 2 intersection points just like that. Okay. Now, the last carbon is not chiral, so we keep the H's with the C. So that's going to go here on the bottom. Okay, that CH3 represents the CH3 at the end of the molecule. For aldehydes, you don't write it usually like a double bond O with the H. You can, sometimes you will see them that way, but a lot of times they're not. Since it is an aldehyde, it's very often written like this, which looks a little weird. Okay, they write aldehydes as CHO. Okay, I know that's strange looking. That's just the way that they're very often written. Not entirely sure why. Okay, and then I have to add everything else. So I know that I have a Cl on both the second and the third carbon. And I also know that I have H's. Okay, so that would be my first picture. And then what you would really end up doing is you're just going to kind of move things around. Okay, they're chiral carbons, so things move. This does not change. This does not change. What I have drawn in red does not change. So, because I have 2 chiral carbons, I know that I can make a total of 4 structures because of the 2 to the n. 2 squared is 4. So here's my first one. I'm going to draw the rest of my basic structures here. I'm going to add my aldehyde group to all 3 of them. And my CH3 group at the end. And now I'm going to move my H's and my Cl's. So I already put both Cl's on the right, so why don't I put them both on the left? And now I'm going to kind of, switch things up, put one H and one Cl on each side. And then, of course, finally, the reverse of that. Okay, so notice I didn't change the length of my carbon chain. I didn't change the non-chiral groups. I left them alone. And I just moved everything else around. Okay. Non-chiral carbons stay together, okay, with their H's and anything else attached to them. All right. So, we did an example. What I would like you to try to do is this bottom one. I'll help you out just a little bit before I pause the video. So I'm going to draw difluorohexane. Okay, and then it's a 3,4, so there's an F here, and there's an F here. Okay, I know the rest of these that I'm drawing in right now are H's. Okay, therefore, when I look at this, this is a chiral carbon, right, for different things around the center. And this would be a chiral carbon for different things around the center. But nothing else would. So this group here, which is actually the same as this group over here, are not chiral, so they would stay together at the top and the bottom of your structure. Okay, you should be drawing a total of 4 because there are 2 chiral carbons. Please pause the video and try that now. Please check your answers. You'll notice what I have labeled over here in purple is what I have at the top and bottom of each of my chains here. This is a CH2, this is a CH3. Because they're not chiral, they stay together. Then I have my chiral carbon, my second chiral carbon, and then of course the other CH2, CH3 group. And then you'll notice that I wrote in blue the different changes that would occur in the 4 options. So F's are on left, right, and split. Okay, this is a good place for us to pause, and I will start our next video shortly.